Hello everyone. Today the topic we're going to discuss is the diffraction patterns and the polarizations. Okay, so in these topics, we're going to talk about what is the diffractions. Okay, we talk about grating, single slit, then the circular apertures, the diffraction of the X-ray by the crystal, and at the end we're going to discuss about what is the polarizations and what is the polarization of the light wave. Okay. As usual, so when I will rearrange a topic so that in the way that I think that the story can go more smooth. Okay, and some formula which is just pop up in the survey, I will prove it a bit or point you to which direction the meaning of that. Okay. Okay, let's start. So we start with the interference first to get an idea, because when we're talking about the slit, basically we treat the number of the, when we're talking about the grating, basically we just treat as a slit with many number of the slits. Okay, for example, n become thousands, 10,000, for examples. Okay. Okay, so before we go to that, we're talking about the interference from 3 slit first. Okay, so we suppose that we have the monochromatic coherent source of light pass through the parallel slit. Okay, the question is that what is the intensities? Can you visualize it? How it's going to look like, and find the conditions of the maxima in the interference patterns. Okay. Okay, so let's start. So you have 3 slit. So basically you're doing the same as the, you have 2 slit. Okay, you just point to somewhere on the screen. Okay, so taking it to the screen like this. Okay, like this. Okay, so now you have 3 ray of light, okay, coming to the screens, and then we're talking about the path difference. Okay, so we are talking about the path difference, talking about the path difference here. Okay, while the distance between slits is d. Okay, this is theta. So same as before, so the path difference, it's which is delta, it's equal to the d sine theta. Okay. Okay, then when we would like to calculate intensities, okay, it's gonna be the same way as what we did before. So let's see what we did before. It should be in one of the lectures, maybe this one. Okay, right. So in that time, when we're talking about 2 wave, right, we start with the wave functions. Two of that. Okay, one is shift by the phase difference phi. Okay, and then we try to sum it, and then we say, yeah, intensity is basically the square of the electric field. Okay, so we're gonna do it in the same way. Okay, so we have the electric field, okay, from the source 1, which is E1. So it's gonna be E0 psi omega t. Okay, and then we have the E2, which is E0 psi omega t plus phi. Okay, so phi is the phase difference. So don't forget that psi functions, so the argument of the psi function needs to be dimensionless, or basically it's radiant, right? But it's dimensionless. So what you put in the psi, it's not the delta, which is the phase, which is the path difference, but we need to talk about the phase difference. Okay. So let's talk about the phi first, maybe. So we know that when the if you have the wave, right, and then you say that another wave is shift by lambda. So basically, if it's shift by lambda, it's mean it will have exactly the same, right? In this case, because it's shift by lambda, so you shift this thing, right, by lambda. So you shift it. Okay. Maybe I just need to write it here. Okay. So it means that you shift it by lambda. So you shift it here, for example. It still be constructive interference. Okay. So in this case, you can know you know that for the path difference lambda, it's compared to the 2 pi of the phase difference. Okay, and in this case, you have d sine theta, so it corresponds to the 2 pi d sine theta over lambda. Okay, so this is the phase difference, and this is what we're gonna use it here. Okay. Okay, and then from E3, okay, E3 is also shift, right? And it shift by 2 delta. Okay, so it's E0 psi omega t plus 2 phi. Okay, so now what is your job? It's you try to sum this. Okay, what exactly it is, right? And then you can say that, okay, the I average is basically E square average. Okay, so we gonna sum it. Okay, it's maybe easy if you sum E first one and the third one first. We need to use a formula, so let me write it here. We have psi A plus psi B. It's equal to the 2 psi A plus B over 2 cosine A minus B over 2. Okay. Oh, sorry. Okay. Right. So we do first E1 plus E3. Okay. So E1 plus E3. So you're gonna get 2 E0 psi A plus B, right? So which is the omega t plus 2 phi and divided by 2. So it's you're gonna get omega t plus phi. Okay. And then you get another term which is cosine. When you do the subtraction of the increments, so omega t minus omega t plus 2 phi, it's going to be minus 2 phi. So cosine minus 2 phi, it's cosine 2 phi, right? And then you divide it by 2, so you get cosine phi here. Okay. Then you can see that you get the E total, which is E1 plus E3 that we did it before, and then you plus E2, right? So you're gonna get what you gonna get? I miss 2 somewhere. No, I don't miss it. Okay. So we're gonna get, this is the same. So E0 psi omega t plus phi. Okay. Then 1 plus 2 cosine phi. Okay. So I, which is expectation of the E square, okay, you're gonna get what you're gonna get you're gonna get E0 square divided by 2, because the expectation of the average of the sine square become half, right? And then you're gonna get 1 plus 2 cosine, and then what is phi? Phi is 2 pi d over lambda sine theta, and then square. Okay, I should say this is proportional. Okay, so what you can see is that if I say I, it's equal. So when you say proportional, you can multiply by a factor, right? Okay, it's 1 square factors, whatever. E0 square divided by 2, 1 plus 2 cosine 2 pi d over lambda sine square by 2. And then when you get I max, okay, it's the same, E0 square over 2. And then for maximums, maximum happens when this term cosine phi become 1, right? When cosine phi become 1, the term in the bracket become 3, okay? And then you square it, so you get 9, okay? So you get 9. So from these two, right, you're gonna get I over I max, okay, which is 1 over 9, and then 1 plus 2 cosine something in the brackets, and then square. Okay, so yeah, this is the solution that we get. Okay, so intensity divided by the maximum intensities will be 1 over 9 2 cosine 2 pi d sine theta over lambda square. Maybe I should, okay, I write it, sorry, I will write it in the way that in the complete way, so to avoid the confusions. I over I max, okay, it's become 1 over 9 1 plus 2 cosine 2 pi d over lambda sine theta, and then you get the square here. Okay. Oh. Okay, so this is what you will get. Okay, then what is the maximums in the patterns? Okay, so you have to answer yourself that when is the maximums? Okay, so the maximums will happen. The maximum will happens when cosine of 2 pi d over lambda sine theta equal to 1, right? This is the concept of the maximum, because then it's make cosine to be 1, and then in the brackets become 9, okay? 9 over 9 is 1, so I equal to I max. So what is the 1? So it means that the angle need to be 0, 2 pi, 4 pi, right? So yeah, because it cannot be pi, because when it become cosine pi become -1, okay, then you will not get the maximum from here. So it's mean 2 pi d over lambda sine theta equal to 0, plus n minus 2 pi plus n minus 4 pi, and so on and so on. Okay. So you get 2 pi, so this become 1, this become 2. So the condition of the maxima is d psi theta equal to the m lambda, where m is 0, plus and minus 1, plus and minus 2, and so on and so on. So this is the condition of the maxima. Okay. So now we try to make a plot, okay, visualize how I look like, okay, and then we're gonna see the detail. I will not plot it, okay, but you can try it by yourself, and you have many tools as you prefer. One which is free and it's online, it's the Wolfram Alpha, so you can put your equation there, okay, and then it will make a plot for you. Okay, so let's see, now it's make a plot. Wow, it's cool. So this is the equation that we already solved. Okay, so it's 1/9 and in the bracket 1 plus 2 cosine, which is a big term, and then this is overall is square. Okay, so this is the how thing it look like. Okay, so you have the big minima, maxima, which is, we call it the principal. So it's the one which is reach 1, and then you're gonna have a small peak here that we in this case we call the secondary maxima. Okay, then we're gonna looking in the detail of the plot. Okay, but just to show you that when you have this kind of complicated functions, try to put it and try to visualize it. Okay, so then you will get, this is the pattern that you will see, and how this thing can be related, and how can you describe it. Okay, the behavior of it. So you don't really need to put it by yourself. I mean, make it on the paper. Just put it in the computers, and you can make it. Okay, it's today the way to learn it. There are several ways to learn that, and several ways to visualize. Okay, so just try on it. Okay, so this is the plot, how the plot look like. So I just make it also from the Mathematica. Okay, you have at the center. Okay, so you can forget about the scale that I'm putting there at the down on the x-axis, but you can say, okay, so this is the central maxima. Okay, so this is theta equal to 0. Okay, d psi theta equal to 0. Okay, then you get another maxima. Okay, and another principal maxima. Okay, but before we go to that, we would like to learn first about the minima. Okay, so we would like to learn here. So this is what? Okay, and this is what also you have 2 minima. Okay, so let's go back to the intensity we get. Okay, so the intensity will become a minima when it's become 0, right? So it's mean what does it mean? It's mean that the cosine of 2 pi d over lambda psi theta, right, need to be half, right? Because when it's become half, so half multiplied by 2, it's 1, right? And take negative minus negative sign, and then 1 minus 1, it's 0. Okay, so you have this minus. Okay, so cosine to have the minus, you have let's say you have the unit circle. Okay, so you project on the x-axis, it becomes cosine theta, and on the y-axis it's sine theta. Okay, so when you get the minus half, it's here or here. Okay, you have two angles which give you minus. Okay, so the first one is 2 pi over 3. This is 2 pi over 3, and this is the 4 pi over 3. Okay, so you will get 2 pi d over lambda sine theta equal to the 2 pi over 3. Okay, you cancel 2 pi, so you get sine theta equal to the lambda over 3d. Okay, and then if it's equal to 4 pi over 3, you're gonna get sine theta equal to the 2 lambda over 3d. Okay, I will need some space, so maybe let me move it a bit. If it's equal to the 4 pi over 3, so you will get sine theta equal to the 2 lambda over 3d. Okay, so yeah, this is the point where you get the minimum. Okay, so you get this point, it's lambda over 3d. This point get lambda 2 lambda over 3d. Okay, then you see, yeah, so this point should be 3 lambda over 3d, which is lambda over d, right? And what is a lambda over d? Right, this is maxima. This is principal maxima, because it's mean d sine theta tau equal to the a lambda. Okay, so sine theta equal to the lambda over d, which is the principal maxima. Okay, now you understand. Okay, so you have 2 points where it's become minima. Okay, and the next principal maximus. Okay, then if you would like to look into the secondary maxima, okay, I will leave it for you to try. Okay, you should get so try. What you should get is the sine theta equal to the m plus half lambda. Okay, where m equal to the 0, plus and minus 1, plus and minus 2, and so on and so forth. Okay, so this is the interference intensity from 3 slit. Okay, before we move next to the general form of the end slit, one thing that I would share to you is also the mixing of the wavelength. Okay, so when you use a monochromatic plane wave, it comes with a single frequency, but if you use the white light, it comes with a several frequency, right? It's ranging from 400 to 750 nanometers. So when you're looking on your result, okay, your result includes also the lambda, right? Because you say yes, the first minima is lambda over d, right? You say that the first minima is lambda over 3d, right? Which means larger lambda, larger width. Okay, this is the case of the red light. Okay, and smaller lambda, smaller width, right? Okay, you see that the width of the blue light, it's smaller than the bit of the red light. Okay, this coming from the single source. Let's assume it's to be white light. Okay, and now it have the component. So you can see that when you have a 3 slit, okay, you can split the wavelength. Okay, so when you're looking through the slit, you will not just see one color, which is the superposition of the all wavelength, but you will see it split as the rainbow colors. Okay. Yep. So this is interference from the 3 slit. Okay. So for interference from the end slit, you can see that this is how it's look like. We summarize it in the next page, but just to see, okay, so this is the double slit. You don't have the secondary minima, secondary maxima. Okay, you have one minima between a principal maxima. When you got 3 slit, you have a little secondary maxima. When you go to 4 slit, you get double. When you go to 5 slit, you get triple, 3 maxima. Okay, so this is the behavior of the end slit. So when you have the end slit, okay, what you will get, it's basically you're gonna get the principal maxima. Okay, it should be equal. Just illustrate that. Okay, and the central one it's either equal to 0. Okay, and then the next one is lambda over d, and next one is 2 lambda over d, and so on and so forth. Okay, so this is the principal maxima. Okay, and then you're gonna have the small one, which is the minima and the secondary maxima. Okay, so how big of the number you're gonna get? Okay, so in this case you're gonna get I would say n minus 1 minima. Okay, n minus 1 minima, or you can say n minus 2 secondary maxima. Okay, you can say n minus 1 minima or n minus 2 secondary maxima. Okay, for example, if n equal to 3, right, so you're gonna get 2 minima and 1 secondary maximum. And this is what you see before, right? So we get this one, you get a small, and then you get a big one again. Okay, like this. Okay, this is how it's gonna look like. Okay, and then you have the width. Okay, in this width that sometimes people can call delta theta, when equal lambda over nd. Okay, so the second one can be lambda 2 lambda over nd, and so on. Okay, and when it's come until n lambda over nd, it's become lambda over d, and that's become the principal maxima. Okay, and then last thing about this, it's about the intensities. Okay, because if you're looking in the intensity formula, you see the factor 1/9, right? This is for 3 slit, okay? So basically the intensities will be proportional to the number of the slit square, okay? So when you have 100 slits, so it's gonna be brighter than the 1 slit for the 100 square, 100 by the factor of the 100 square, okay? Why is it in that case? Because first, when you have more n, right, it means you have more sources, okay? Because each slit is a source of the Huygens principle, right? It's a source of the wave, and then this source will be interfere to each others on the screen. So if you have more n, you have more bright from the source, okay? And then if you have more n, you have less width, right? Why? Because when you have more n, when n is large, the width gonna become small, okay? So you have the width here, right? And then when you have more n, what's gonna happen is that it will shift up, okay? And you're gonna have here. So the width gonna be reduced when you have more number of slits, okay? So that's why sum up in the intensity, we're gonna depend on the n square, okay? Then I don't, if you understand this behavior, okay, this phenomena, we don't really need to talk about this the grating at all, because the grating is basically you treat the large number of slits to become a grating, okay? We're gonna review the grating in the exercise class, so don't worry about that. Just to let you know that for the grating, everything is done, it's proved by the number of the end slit, and then you take a big n, okay? Then you will get a grating phenomena. Okay, so whatever you proved before, it can be used by the grating. So the condition for the maxima become d psi theta equal to the m lambda. You know the first and the first minima. So to determine the width of the principal maxima. Okay. Yep. So this is all about the interference from the end slit and the behavior of the grating. Okay. Okay, ครับ so we move. So now at this point, right, you can basically describe the phenomenon with the multiple number of slits, okay? But the question's back to that, and if we have just one, what's going to happen, okay? And that's what we call the diffractions, okay? So imagine that you have a tunnel, a hole, okay, and then we have the wave pass, okay. Basically the wave should just go straight in this way, right? You should not be able to detect the wave that behind the obstacle, behind the object, right? You should just see the wave that can pass through the hole. But this is not true. It's not what we see, right? We can see the wave here, even here, that behind the barrier, okay? So that is the phenomenon that we call the diffractions, okay? And to remind that when we start to see the diffraction, basically it means we start to consider the wavelength will reach in the order of the slit, okay, of the hole that we are talking about, okay? when you have a much larger wavelength compared to the whole, you will see more spreading. Okay. In the diffractions, we need to, let's say there are two main situations. So the first one, we call it the far field diffraction. Okay. What the far field means is that you have the hole and then you have a screen or whatever detector you have, but it's far enough that you can consider that the wavelength, the wave that coming out from this hole, each point of this, each point in this hole, which behave as the secondary source in the Huygens principles, will traveling in the parallel, right? Okay, so what I'm saying is that, so you have the hole, and then in the hole, you see you have the source. This is the Huygens principle, right? So in the Fraunhofer diffraction or the far field diffractions, it means that you approximately all of this one parallel to each others. Okay, so this is the case of the Fraunhofer diffraction, and this is what we're gonna learn in this class. Okay, all right rays are approximately parallel to each others. We consider the situation with a long distance from the diffracting object. Okay, and there is another case which we will not discuss in this class, is the Fresnel diffraction. Okay, so the diffraction patterns are created near the object. Okay, so we look into the single slit diffractions. Okay, so the situation is that when you have the diffractions, this is what you see from the experiments. Okay, so you see the the bright fringe in the center, and then you see the dark and then a small fringe, bright fringe next to the brightest one. Okay. Okay, so now we will discuss about this. So let's start with the slit, the single slit. Okay, you have this one as a slit. Okay. To understand the situations, we divide the slit into two halves. Okay. Okay, so we start with we split the slit into two halves. Okay. So for example, I assume that the first half have 4 light source. It can be 5, it can be 100. Right? You can divide it whatever you like. Okay, just to visualize the idea of what we are thinking about. So you have 1, 2, 3, and 4. Okay, and in the second half you have 1, 2, 3, and 4. Exactly the same. Okay. Then you have the screen somewhere here. Okay. So we consider the dark fringe. Okay, the minima. Okay, so we pair it. The size. Okay, the size of the slit. It's A. Okay, the size of the slit is A. Okay, so half of that is A over 2, and this is A over 2. Okay, so I use A for the slit width. Okay, sorry, and I use D for the distance between slits. Okay, between slit. Okay, this is what the parameter that it's used in survey. So I try to follow this one. Okay. So we consider the dark, the first minima. So it's somewhere here, for example. Okay, and then you pair it with the first one on the. Oh, sorry, the first one in the lower half. Okay, like this. Okay, so you see that this is the path difference, right? And then the path difference is what? It's a over 2 sine theta, right? This is the path difference. Okay, then you say, yeah, we consider a dark fringe a minima, so it's mean that the a over 2 sine theta equal to the lambda over 2. Right? Then you see that you get a sine theta equal to the lambda, and this is the same if you try to match, for example, 1 and 5, 2 and 6. This is, I mean, the source we are considering. Okay, 3 and 7, 4 and 8. Okay, this is exactly the same. Right? Okay, so now you get an idea. Yeah, this is something that it can be a minima. Okay, then if you're talking about the next one and the next one and next one, you can see the general conditions for the destructive interference. Okay, as follow. You're gonna get the a sine theta equal to the m lambda, where m become plus and minus 1, plus and minus 2, plus and minus 3, and so on and so forth. Okay, so this is the conditions of the destructive interference. Okay, condition for the minima. Okay, and be careful, because the formula it's very like the constructive interference of the constructive interference in the double slit. Okay, it's very close, but it's different. Now we are talking about single slit diffractions. Okay, that's why I put the A here, and theta cannot be 0. Okay, theta equal to 0, it's the bright fringe. It's the central bright bright fringe or the maxima. Okay, yeah, so this is the single slit. Okay, so now we need to understand about the this intensity of the single slit. Okay, sorry, yeah, correct. I'm confused with, so yeah, we need to talk about the intensity of the single slit. It's gonna be a little heavy proof, okay, but we try to go through that so that you see the idea of how this formula is formed, because in the book it just gives you this formula. Okay, it's sometimes it's gonna be difficult to understand, so I think that it's maybe better if I'm trying to give you an idea of how we can deal with this thing. Okay, there are several ways to do this. Okay, it's not necessary to do as I have done, as I will do here. Okay, but what I will do here is basically based on the trigonometry only. Okay, with some trick to switching some parameters. It will be more easy if you use the complex number, and then if you form the complex number, I will point it later, then your life gonna be much more easier than what I'm trying to do here. Okay, but yeah, I see the lecture we do the weird things first, and then we forget about it forever. Okay, just that you see that this thing can be done in this way, so it's something in your memory say that yeah, this is possible to be done. Okay, so we have the a single slit. Okay, with the width A Okay, and we have the screen. Okay, maybe I short it a bit. Yeah, you can always shorten the screen. Okay, and then the question is that, yeah, but if we short that, it's gonna be, it still be Fraunhofer. The answer is it can be Fraunhofer anytime if you put the lens here. Okay, because the convex lens will convert the light. Okay, so you don't need to go very far to get the patterns, but you can go closely. Okay, so you're gonna have the convex lens here. Okay, to convert the light ray. Okay, then okay, so then we're talking about the first light from the first source is going to the lens. Okay, then it's converged somewhere here. Okay, and the second light is going also to the lens, and then it's converged to this one. Okay. So now we will say, okay, we're gonna have n source. Okay, what n source is? So the number of the source that we are talking about here, it's n. Okay, so it means that the distance between source become what's it, a over n, right? So the distance between source equal to the a over n, right? So we try to zoom, okay? We zoom it, so you get two source, okay? You make the light happen, and this is a over n, okay? And then you have this phase, this path difference delta equal to the a over n sine theta, right? Okay. Just check if I do it correctly. Yeah, I do it correctly. Okay. Just in my lecture, I put this one, I call a over n, call the delta y. Okay. It doesn't, I mean, you can keep a over n all the time. You just need to write a over n, a over n, over n. Several times you make it, so you can just write it in a number, just one parameters. So I put it as a delta y. Okay. So what is the phase difference in this case? So the phase difference will be, so you have, if you have lambda, it's going to be 2 pi. If you have this thing, going to be the delta y sine theta 2 pi, right, divided by lambda. Okay, so this is the phase difference. Okay, let's color it. Okay, then we start the same as slit. So we're talking about the E. Okay, so you get E1, it become E0 sine omega t. Okay, this is E1. Now E2 become E0 sine omega t plus the phase difference. Okay, let's call it delta beta. Okay. E3, right? So same E0 sine omega t plus 2 delta beta. Okay, and so on. And you get En equal to the E0 sine omega t plus n minus 1 delta beta. Okay, so your job is sum of these, right? E total equal to the E1 plus E2 plus so on and so forth until En. Okay, and then intensity gonna be expectation, average of the E total square. Okay, so this is the way you have to do. Okay, this I think at least you should reach this point. Okay, after this it's gonna be on how to solve it. Okay, but just one note is that the phase difference, the total phase difference, let's say the total phase difference okay become n delta beta. Okay, so you get n, and then you have 2 pi over lambda. Delta y become a over n sine theta, so n it's cancel. So you get 2 pi over 2 pi a over lambda sine theta. Okay. Okay, let's try to solve it. Okay, we try to solve the this trigonometric relations. So we start with the trigonometry relations. So we use cosine of a minus b minus cosine of a plus b. Okay. Okay. What is it? It's equal to the 2 sine a sine b. Okay. Okay, so let's start. So we first start with the cosine of omega t minus delta beta over 2, then minus cosine omega t plus delta beta over 2. Okay, so a with omega t, b is delta beta over 2. Okay, so you will get 2 sine omega t sine delta beta over 2. Okay, so this is the first one. Then the second one, you say you start with the omega t plus delta beta over 2 minus cosine omega t plus 3 over 2 delta beta. Okay, and you ask, but it's not different. It's different. This is not a and b, right? But just to look at it closely, these terms, okay, what is it? It's omega t plus delta beta, right, minus delta beta over 2. This term is cosine, this term is the omega t plus delta beta, and then plus delta beta over 2. Okay, so this is A, this is B. Okay, this is A, this is B. Okay, so what you get is 2 psi of omega t plus the delta beta, and then psi delta beta over 2. Okay, let's do the next one, and then we do to the final one. Cosine of omega t plus 3 over 2 delta beta minus cosine omega t plus 5 over 2 delta beta. Okay, so in this case you can see, okay, so this is the same, so this term look like the omega t plus 2 delta beta minus delta beta over 2. This term omega t plus 2 delta beta plus delta beta over 2. Okay, this is A, this is B. Okay, so you get 2 psi omega t plus 2 delta beta psi delta beta over 2. Okay, and now you see, you have omega t plus delta beta, omega t plus 2 delta beta, right? This is the term that we looking for that. So it means if you sum up on the right, you sum on the left. Okay, and you will see also that this term will be cancelled to each others, right? So it means you're going to have the first term and the last term only. Okay, and then you divide it by psi delta beta over 2, you get what you would like to have. Okay, so what is the final term of this one? You can write the last term, okay, as the cosine of the omega t. It will be n minus 1, right? Yeah, plus n minus 1 delta beta minus delta beta over 2 minus cosine omega t plus n minus 1 delta beta plus delta beta over 2. Okay, so it's become 2 psi of the omega t plus n minus 1 delta beta psi delta beta over 2. Okay, so this is the term that you would like to give, you like to get. Okay, and the term in between is cancelled. Okay, so now you have the first term and the last term. Okay, so what you will get is that you're gonna get cosine omega t minus delta beta over 2 minus cosine over t plus n minus 1 delta beta, right? So equal to the 2 psi delta beta over 2 and multiply it with the last term that we are trying to find, psi whatever, that sum up together. Okay, so now we need to do more complex reduced form of that. But now you got you are more than halfway of that to be done. Okay, so the right term is what we get already. Okay, so we need to manage the left term. Okay, so for the left, you can use the cosine A minus cosine B. Okay, cosine A minus cosine B is minus 2 sine of the A plus B over 2 and the cosine of A minus B over 2. Okay, so what you will get, okay, let me write the right term first so that we will not end up in something that at the end. So we're gonna do delta beta over 2, and then this is something that we would like to find. Okay, equal to what? Equal to the minus 2 of the sine. So you sum this thing. So it's the 2 omega, right? And you will get, just make sure that I don't forget something stupid. Yeah, I think I did a small I did some bug here. So n minus 1 and then plus, so it needs to be half. Okay, right, this is n minus 1 and then you get plus half. Okay, so you get n minus half here. Okay, so you get 2 sine of the omega t. Okay, plus, so you have n minus half and then minus another half, so it's become n minus 1. Okay, right, yes, no, yes, just a second. Okay, that's correct. The delta beta and then you divide it by 2. Okay, because 2 it's from here. Okay, and then for the last term, cosine A minus B, so omega t minus omega t, it's cancel. Minus half of this one and then minus of this one, you get minus n, and then you plus half here, so it's cancel, so it's become minus n. So cosine of minus n, it's n. Okay, so you get n delta beta over 2. Did I wrong? Did I get something? Just a second, I'm check the trigonometric formula again. Maybe something wrong when I try to write it. Right, yeah. Sorry, I think I did wrong in one place, which is this is psi. Okay, this is psi. Great. Okay, so now we can cancel 2, and then when it's psi, the minus here, the minus will be cancelled here. Okay, so what you have is psi of the omega t plus sine of the omega t plus delta beta plus whatever, okay, it's equal to the sine of the omega t plus n minus 1 delta beta over 2 sine n delta beta over 2 divided by sine delta beta over 2. Okay, then you want to have the amplitude of the electric field, so you multiply by E0, right? So that's easy. You can put E0 here. Now you have it. This is the E total. Okay, so you can try to manage it. So I, it's proportional to the average of E total square, right? So it's become E 0 square divided by 2, and this 2 is the average of the psi. Okay, so you get psi square n delta beta over 2 divided by psi square of the delta beta over 2. Okay, so now you have that. So you need to manage the term. Okay, so the denominator term, okay, n delta beta, you have it already. The n delta beta, it's here, which is 2 pi a sine theta over lambda, right? So divided by 2. So the first, the denominator become sine square of the pi a over lambda sine theta. Okay, this is the denominator. And then for the denominators, okay, we can approximate that the delta beta it become small. Okay, so we can do the small angle approximations. Okay, so then it's become delta beta over 2 square. Okay, so now what you can do is basically you can multiply it by the n square and divide it by the n square. Okay, and then you can absorb the n square term to this one, right? And now you see that the amplitude gonna be start to increase. Okay, but that's why, I mean, we don't need to care about that because we can absorb it to be the maximum. Okay, and then so you get on the denominator of the denominator here, and delta beta, it's become pi a over lambda sine theta square. Okay, because you get n delta beta over 2, so this is the same here. Okay, so finally, so this is what you will get. You're gonna get I equal to the I max. Okay, and then the denominator term is psi square pi a over lambda sine theta, and then the denominator term will be pi a over lambda sine theta to the power of 2. Okay, so yeah, now you have the intensity of the diffractions. Okay, now you have that. And then when you prove this, you have to make sure that how this thing is right or not. So you can try to find the minima conditions, right? So the minima conditions gonna be you can make the size square become 0, right? So size becomes 0. So it means so if you're talking about the minima, right? So you're gonna get psi of pi a over lambda psi theta become 0, or you get pi a over lambda psi theta equal to the m pi, right? And then you can write as normal m equal to 0, 1, 2, 3, whatever. Is this correct? Yeah, just be careful. It's maybe not correct. Why? Because if you take m equal to 0, okay, so it means pi a over lambda psi theta becomes 0. So the nominator term becomes 0, but the denominator term will also become 0. Okay, so it's 0 over 0, it's not 0. Okay, just be careful that you need to do the differentiate to find the limits of that. Okay, but it's not in this course. Okay, that's calculus. You can do that. So yeah, you cannot use this one. Okay, and then if you use 1, what happened? If you use 1, you're gonna get a m equal to 1. So you're gonna get a sine theta equal to the lambda. Okay. So this is what you get before, right? A sine theta equal to lambda equal to plus and minus 1, plus and minus 2, and so on. Okay, and you see that from this formula, you never talk about a sine theta equal to 0. Okay, so let's be careful. Okay, great. So now you have the intensity of the single slit. Okay, so what you should do is now you combine it together with the interference patterns. Okay, so what you can do is basically you say that when you have a slit, the double slit situations, so I just change this the slit width to become A, so it's the same as the formula we are using, and the distance between slit is D. Okay, so the intensity is gonna be multiplication of the interference pattern. Okay, this is from the last topic, pi d phi theta over lambda. Okay, and then you have psi pi a over lambda phi theta divided by the pi a over lambda phi theta square. Okay, so the first term is coming from the interference. The second term is coming from the diffractions. Okay, so this is what you will get at the end. Okay, so it look like you overlay the interference patterns, and then you make an envelope of that by the diffraction patterns. Okay, and then you will get this kind of the diffractions, interference or diffractions fringe. So it's gonna be bright in the middle, and it's gonna be bright but lower dim and lower dim, and go to 0 again, and then go up a little up, and then go down. Yeah, so this is what you will get. Okay, then we can ask the question that we would like to find the place, okay, where where is the first minimum of the diffractions, okay, where it is, and which m that correspond to the interference. Okay, so we are talking about these positions. So this position is minimum from diffraction. Okay, and we say, okay, and in this place, what is m? Okay, so let's say what is the bright interference pattern? Okay, m is the m bright interference pattern. Okay, so we make the conditions happen. Okay, so you have d psi theta equal to the m lambda. So this is from the interference. Okay, this is interference. You have a psi theta equal to the m lambda. This is from the diffractions, right? And at that point, it's the same place, right? So you can just divide it. So you get d over a. Did I get something wrong? Sorry, a psi theta equal to the lambda, because it's the first place. Sorry, it's the first diffraction, right? This is the first minima of diffraction. Okay, so you get you will get d over a equal to m. Okay, d over a equal to m. Okay, so it's mean it's gonna be how many fringe, how many interference fringe gonna happen. Okay, it's gonna happen m times, right, on the left, and then m time on the right. Okay, so at the end you're gonna see that so this is central fringe. You're gonna see, yes, from central to the first point of the minima you have m fringe, and from the central to the first point of the minima on the lower side you get m fringe. Okay, then total fringe in the central maxima will be 2m. Is it correct? You have m on the top, you have m in the bottom. No, it's not correct, because we have only one central, right? So you need to have minus 1, okay, because we have only m, we have only one central. Okay, so the total fringe in the central maxima will be 2m minus 1. Okay, so this is what we're gonna get it. Okay, so I take one example as the last one. So we're talking about the 2 slit. Okay, so in this slit we use the light with the 650 nanometers light wave, okay, passing of the 2 slit, okay, which slit width become is 3 micrometers, and the distance between 2 slit is 15 micrometers. Okay, so 15 it's d, right, the distance between 2 slit. So you have 2 slit here, so the distance is 15 micrometers, and the distance, the size of the slit is 3 micrometers. Okay, so this is A. So you get D over A equal to the 18 divided by 3, so it's 6. Okay, so it's mean that you're gonna have the total fringe 2 times 6 minus 1, which is 11 fringe. Okay, and then you can looking in the figures. This is what represents the interference diffraction pattern you see, and then you count it. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then this become the first minima. Okay, so now you can describe the substructure under the diffraction patterns. Okay, great. I think we will stop here. So the next class we will review this a bit. We're talking about the I think the slit is most done. We're talking about the circular apertures. We're talking about the separations efficiencies, and then we're talking about the diffraction of the X-ray, and at the end we're talking about the polarization of the wave. Okay, so it's maybe take another hours to finish these diffraction stories, and then next week we're gonna start with the special relativities. Okay, which maybe it takes some time. So maybe I'm thinking maybe 3 hours or 4 hours to complete that. Okay, so I think this is done for today. Try to review this. Try to understand the step you are doing. Okay, don't just use the formula. Understand the formula. It's much better than just try to use it, because if you understand, you can apply to several questions. Okay, so thank you very much, and see you next video.